Okay, so it's time for the 10th lecture of the series. So this series we refer to as Nasi Women in Science lecture series. It was started almost 2 years back, and to commemorate the eve of 75th year of independence. And it was part of Nasi's social initiative and Science for Society initiative. And initially it was thought that these lectures will be arranged in such a way that it can encourage young women scientists and young researchers, PhD students, and undergraduate students, postgraduate students to continue main course science and research, and to encourage them that it is doable and people can do it. The idea was to request established women scientists to deliver this series of lectures. But of course, these lectures are not restricted to girls students only. So all the students are expected to be encouraged and carry a confidence that they can also do good research. They can also contribute to society by performing research or science and technology. So without going much detail of the idea, because many of us are attending these lectures from the beginning and familiar with the idea and Nashi's initiatives, but some of the students are new. Some people have joined MSc now and they are in this meeting. So keeping them in mind and to allow them to know that what NASI is and what are the NASI's science and society initiatives, so that they can connect to NASI and do the similar, join in similar programs in future also. I would like to request NASI Delhi chapter's chairman, Professor Anurag Sharma, who was a professor at IIT Delhi, to say a few words about the NASI Delhi chapter and its initiatives related to science and society. Professor Sharma, please.
Hello. Yeah. Okay, Anirban, thank you. It's my pleasure to welcome you all, particularly Professor Vindhya Arora from Canada, who's going to give the talk today. And NASI is the first scientific academy which was established by Professor Meghnad Saha in Allahabad in 1930, and it has been functioning since then. And it is particular focus is on science and society, and that is why we do programs involving women or school and college students, and variety of various segments of society where the science should reach and from where the science should come, both ways. And it is generally done through the chapters. NASI has, it's called National Academy of Sciences in India. That is, short form is NASI. And NASI has 21 chapters spread across the country. And Delhi is one of these chapters, and Delhi is one of the very active chapters. And it's active because of people like Papia Chaudhary and Anirban Pathak, who keep organizing programs, and many others in different colleges, institutions, universities. And this program particularly is under the Science and Society program of the NASI, and it has been, as Anirban said, that has been running for 2 years. It's a very successful program, and we have I think there is somebody yeah. So we have in this series we have today's lecture, which is on a very, very important topic, which is connected with quantum technology. Quantum technology is these days is at the forefront of science and technology everywhere. In India also, we have a big national quantum mission where a lot of activities are being done, a lot of money is expected to be put in, and so on. So it's a very important topic, and we are all eagerly looking forward to listening to this lecture. Thank you.
So thank you, Professor Sharma. And I just want to note that UN has declared 2025 as the International Year of Quantum Science and Technology. And the year has just started, and this is the first lecture of this series, and in the 2nd January, and it's very nice that we are organizing this lecture on this topic. So now I would like to request co-host of this program, and my colleague, Professor Papia Chaudhary, to introduce today's speaker, Dr. Bindya.
Okay, welcome all. So without further delay, let me introduce Dr. Bindya Arora. So it is a pleasure to introduce Dr. Bindya Arora today as our guest speaker on this 10th lecture of Women in Science lecture series jointly organized by Delhi chapter of NASI and JP Institute of Information Technology. At present, Dr. Bindya Arora works as a PSI fellow at the Perimeter Institute of Theoretical Physics in Waterloo, Canada. She has been a faculty of physics in Guru Nanak Dev University, Amritsar since 2011. Prior to that, she did her PhD from the University of Delaware. Dr. Arora has worked as a guest scientist in IOP Beijing, China. She has also worked
Hello.
Please mute yourself.
All who are not speaking, please mute yourself. Professor Chaudhary, please continue.
Okay. She has also worked as research fellow in ISAR Mohali. She is a theoretical physicist whose interests include atomic physics, quantum information, and the popularization of science. That is a very important part. Her topic today will be quantum futures, advancing technology with ethics and communication. So welcome, Dr. Arora. And now over to you.
Thank you so much, Dr. Pathak, Dr. Sharma, and Dr. Chaudhary. Thanks a lot for this wonderful start of the new year, and have a very happy new year to everyone here. And I am so glad that NASI's social initiative with all these events organization, it kind of resonates with the topic I'm going to present today. And I'll talk about quantum technologies, but my talk would be more on the responsible development of quantum technology. So I'm really glad that it resonates with the ideas and ideologies of NASI as well. And also with Professor Pathak, I agree that involving more men in women in science is the need of our right now. Like, we need more men to be more aware of why it's important to have women in science. So thank you so much. And maybe I can start with my presentation. First of all, thank you for... Okay, can I start?
Yes, please continue.
Okay. So I'm really glad, and thank you everyone for giving me this opportunity to talk about this very less seek topic in quantum technologies. And quantum has been making headlines, especially with the announcement of National Quantum Mission, and this year being declared as the quantum year. So not only it's a topic of discussion among scientific community, but also among general public. Like this year when I visited my parents, I was so excited to see that they were talking about quantum, which is like really unusual. So as I said, today I would briefly explain about my work and the other quantum technologies being developed. More attention would be paid to the responsible development and deployment of these technologies. And in the first part of my talk, I will just present a brief overview of the research being conducted in my lab, supporting various technologies. And second part would be broader, and I'll focus my thoughts on how this technology should be developed responsibly. So I took the liberty of changing the topic to more like responsible development, to rather than ethics and communication would be a part of responsible development of quantum technology. Okay, so I'm a faculty at GNDU. I'm currently on leave. It's a university in the state of Punjab in Holy City, Amritsar, which is very well known for Golden Temple. Currently, I'm on leave and I'm working at Perimeter Institute for Theoretical Physics. It's an independent research center in foundational theoretical physics located in Waterloo, Canada. This is my group at GNDU and part of it also here at PI. It consisted of 8 PhD students. 7 of them have already graduated. Vipul is a student who is currently with me at PI. He's an international visiting graduate student. And we have been working here since past 2 years. We have had about 30 to 40 master's students in our group who have graduated, and they are following their scientific careers at various research institutes and universities across the globe. And also, I would like to acknowledge various funding agencies who have supported my graduate students who worked on various projects, a part of which I'm going to discuss today. So my background is atomic physics, and my group has been involved in calculation of atomic structure calculations to support various fields spanning from astrophysics, sensors, supporting quantum technologies. Like Jasmeet and Mandeep, they calculated a number of radiative properties for various atoms and ions for their applications in astrophysics. Part of my work also involved working with quantum sensors. Last year, with a theoretical group at GNDU, we proposed a quantum sensor to measure the amplitude and frequency of microwave fields using electromagnetically induced transparencies in Rydberg, rubidium, and cesium atoms. One of my students, Maninder, work was related to, part of her work was related to Rydberg atoms, where she studied the resonant energy transfer of energy from the Rydberg atoms trapped in a linear chain. And we showed that this dipole-dipole mediated transition, it's transferred from the first atom to the last atom with very little absorption in between the intermediate atoms. So it kind of works like a classic quantum Newton cradle. 2 years back, Harpreet, one of my students, she worked with the experimentalist at Guru Nanak Dev University, and they proposed a workable, portable, self-powered magazine-based ammonia gas sensor. Now, the traditional gas sensors, usually they use metal oxides, which have high operating temperatures, which obviously doesn't support the portability design. So in this proposal, a triboelectric generator was attached to the magazine-based sensors, which powered the sensor through human movement. Also, during her PhD, a major part of Maninder's thesis was to study quantum revivals and collapses. She studied, in one of her work, she studied the time evolution of a quantum state in optomechanical oscillator with nonlinearities. She calculated the revival time of the quantum state, where it could be revived and can be used as a quantum memory for quantum communication. And Sukhjit's major part was proposing various trapping schemes for cold atoms to reduce the schematics in the experiments. Jyoti graduated last year. Her work was related to atomic clocks, and she gave a few proposals in terahertz clocks, which I'll be talking about today. And Harpreet and Kiran's work was more calculating dispersion interactions between atom-atom, atom wall, and atom nano structures. Like in one of their works, they studied the interaction between toxic gases like cadmium, mercury, lead, and zinc with the graphene and single walled nanocarbon tubes. And recently, we also studied the effect of higher order corrections in these dispersion interactions. So this was just a brief about what my research group has been involved in the past, I would say 10, 12 years. And before I dive into the details of the quantum world and quantum technologies, I would like to start with a very brief history of the beginning of quantum physics, which is very well known, but maybe it's important for some of the non-expert audience today. So in 1800s, late 1800s, many people thought that we had figured out almost everything about physics with only a few small gaps to be filled in. And in a 19th century, problems like the ultraviolet catastrophe showed that classical physics couldn't explain everything. In 1905, Albert Einstein, with his revolutionary and game-changing papers, introduced concepts like relativity. And we realized that even the Maxwell equation, which we thought was like the peak of knowledge, they contain hidden clues about speed of light being constant. So scientists were unsatisfied with the explanations which classical physics was giving at that time, and unsatisfied with these explanations about these strange findings of particles, physicists developed a new system of mechanics to describe what seemed to be a quantized, uncertain, and a probabilistic world. And one of the major questions quantum mechanics addressed was the nature of light. So in 18th century, physicists believed light was a particle, and 19th century physicists proved that it had to be a wave. But in 19th century, physicists proposed that particle of light, which they call as photon, was explained using probabilities that could be represented as wave. So that was a probabilistic model. And these probabilities could even interfere like the waves did. And building on these new concepts or new ideas, new quantum ideas about the behavior of quantum particles, Bell Labs, the researchers there, they created the first transistor. And this was something which I term as the transition from quantum understanding to the first quantum revolution. And in fact, this word as quantum revolution was first coined by Dowling and I think Milburn, I don't remember, but it was a 2002 paper where this quantum revolution term was first coined. In 1960s, optical physicists, they knew from their knowledge of quantum physics that hitting certain kind of atoms with a few photons at right energy could lead them to emit more photons with same energy and direction as the initial photons. And this was the quantum invention, which is laser. So in the first quantum revolution, scientists were using their understanding of quantum mechanics to create new tools that could be used in classical world. And quantum revolution, the first one, didn't make full use of quantum mechanics, I would say. The full richness of quantum mechanics wasn't really accessible. It was in 1960s when John Bell, he shook the foundation of quantum mechanics, where he proposed that entangled particles were correlated in a strange quantum ways, which could not be explained with the so-called proposed hidden variable theory that time. And we'll talk about quantum entanglement a little bit briefly further, but even if you don't understand what quantum entanglement is, the important point here is that this was an onset of something revolutionary. The other critical ingredient for quantum revolution, the second one, was information theory, which was blend of the quantum science, computer science and mathematics developed by Alan Turing and Shannon. And in 1994, combining these into insights, mathematician Peter Shor, he introduced a fast factoring algorithm for quantum computers. So to summarize, I would say that while inventions like transistors, lasers, they required knowledge of quantum mechanics, the device, they were itself not delicate quantum states. So they could be described semi-classically as well. Quantum technologies like quantum computers, which we are going to talk about, on the other hand, required delicate quantum connections like superposition, entanglement, and so on. But skeptics, they were doubtful that due to this fragility of quantum systems are really, really fragile. They thought that even quantum computer was not even possible. The kind of exponential increase that quantum computers they give, they actually counteract exactly by the exponential sensitivity to the environment quantum systems they have. But in 1995, by combining the concepts of classical theory with quantum mechanics, he showed for the first time that even delicate states of quantum computers could be preserved. And this introduction of quantum error correction was a major push in the field of quantum computing. And beyond quantum computing, second revolution, where we are at present in, also relies on new ways of using quantum mechanics to manipulate matter at quantum level. Like, for example, matter wave interferometers, they exploit the fact that not just light has wave function, but we can also measure phases of atoms which have a shorter wavelength than light, and they could give us high control to experiments in an attempt to measure even smallest effects like gravity could be effect of gravity could be measured using these interferometers. And the next, I would say, ingredient for the second revolution was the precise control, trapping, and cooling of atoms, which led to the emergence of quantum technologies. So I would say that second quantum revolution was a kind of paradigm shift. It gave us the potential to harness the full potential of quantum physics by building these quantum technologies, which are so much being in use these days. So these quantum technologies, they use principles of quantum mechanics like superposition, entanglement, to develop applications which have transformative potentials. And these technologies, they span in very several domains like quantum computing, quantum sensors, quantum networks, quantum communications, and simulators, and so on. So broadly, quantum technologies, they are divided into three categories: quantum sensing, quantum communication, and quantum computing. Like some research groups, they break it into 4 groups. They divide quantum simulators, like they separate quantum simulation from quantum computing. Quantum sensors, they detect movements and changes in electromagnetic fields, and they have immense application in medical imaging, positioning, and navigation. Quantum communication, on the other hand, it enables highly secure transmission of data through quantum cryptography. Now, in traditional message transmission, messages can be intercepted without detection. They could be eavesdropping. And encryption methods, although they have evolved over years, but so have the eavesdropping skills evolved. But quantum cryptography, on the other hand, is inspired by the same concept that quantum systems are really fragile, and the messages, they self-destruct upon reading. So these messages, they are transmitted using these fragile quantum systems, and this fragility is the key to quantum communication. Now, in today's talk, I would talk more about quantum computers, which fundamentally work different from classical computers, and instead of bits, they operate on quantum bits or qubits. They can exist in superposition. This combined with another property called entanglement, where qubits, they are related to each other in a non-classical way. This allows potentially quantum computers to process informations at rates exponentially faster than the classical computers. So there are a number of proposals to build quantum computers. And one of the proposals, it involves Rydberg neutral atoms. And in one of these proposals using these neutral atoms, it's required that these atoms are trapped and controlled using electromagnetic fields. And usually people use lasers to control them. And it turns out that we as atomic physicists, we can calculate the interaction of atom in these electromagnetic fields to manipulate them. Like we can use these calculations to cool them, to trap them, and to precisely control them. And one of my students, he worked on this optical trapping and optical dipole traps for atoms and ions. So optical dipole traps, it offers a very, very handy or versatile tool, I would say, for manipulating the quantum systems. And these can be used to build various quantum technologies, not just quantum computers. The process works as follows. So when an atom is exposed to an electromagnetic field, like say laser, it induces a dipole moment. The interaction energy between the dipole moment and the electric field which has been applied, it creates a potential well. And the atom is, with the cold atom, is kind of trapped in that potential well. Now it turns out that the trapping depth of the potential is proportional to the Stark shift. That's the standard quantum mechanics. Or we can also say that it's proportional to the polarizability, because Stark shift is related to polarizability directly. And thus, since Stark shifts are dependent on the state of the atom, the trapping depth is also state dependent. So in other words, I would say the potential experienced by an atom in an optical trap depends on the atomic state in which it is present, which definitely affects the efficiency of trapping experiments. For example, if I have an atom in state A and I use a laser of some wavelength to trap it, it sees a potential UA. It is trapped in that optical dipole potential. But let's say the need of the experiment is that I make a transition from state A to state B, which is very common for quantum computing experiments. Like you need to transit the atom from one ground state to excited state. So in the other state B, maybe the same wavelength of laser, it is not able to generate the same trapping potential for the system, and the system sees some other potential UB. And it's highly likely that this UB potential is not enough to trap the atom, and my atom is kind of lost from the trapping scheme of the experiment, which affects the fidelity of the experiment. So what we need is a trapping wavelength which would trap our system irrespective whether it's present in state A or state B. And these wavelengths by researchers, a group of researchers, like with the lead of Katori and his co-workers, they suggested that these laser wavelengths where the atoms would be trapped, irrespective whether they are in state A or state B, they termed them as the magic wavelengths. And it turns out that as atomic physicists, we can calculate these magic wavelengths for state insensitive trapping of our atoms by calculating the polarizabilities. So for example, I calculate the polarizability for atom A as a function of wavelength and polarizability of atom B as a function of wavelength. The wavelength where these polarizabilities would match would actually give me the wavelength value where the AC Stark shift experienced by the atom is independent of state A and B. It's same for both the states, hence leading to the equal trap depth for the state, irrespective whether it's present in state A or state B, it will see the same trap depth. So in past, using these calculations for wavelength dependent polarizabilities, we have identified wavelengths for various alkali atoms and alkaline earth ions to simultaneously trap them in ground and excited states, calculated magic wavelengths to trap two different atomic species together in the same trap, which has very useful applications for sympathetic cooling of fermion-boson mixtures. Also proposed something called bichromatic trapping of atoms. So in that, we use two lasers, a control and a trapping laser instead of just one laser for more control of the trapping. And we also gave something called the true note or the magic zero wavelengths, where the atoms, so these are the wavelengths where the atom does not experience any net force in the optical trap. In our group, we also just do not do calculations to support quantum technologies by making these calculations, but we also try to propose new quantum technologies. Like Jyoti worked on something called atomic clocks, and building on our ability to calculate these atomic properties for different atoms and ions, we have proposed these atomic clock designs and analyzed the systematic shifts existing in these atomic clocks. And it turns out that these atomic clocks have potential to be used as very excellent quantum sensors. Now, in order to build any clock, what we need is just two components. One is an oscillator, which exhibits regular periodic events occurring at constant frequency. And then we need an external counting device or a divisor, which can count these cycles of frequency. So once these cycles of frequencies are counted, we can check how many of these cycles of frequency would correspond to 1 second. And it turns out that transitions in atomic systems, they can act as idle frequency standards because an atom is exactly identical to another atom of the same species in same conditions. But since these transitions, they don't necessarily happen at regular intervals, one tunes an external oscillator to this transition frequency. And in our cases, mostly in the cases, these external oscillators are laser frequencies. So we tune in the laser to these laser frequency to the frequency of the atomic transitions, and then just count how many such oscillations or transitions in laser would correspond to 1 second. That's how we define second currently. Now, the current definition of second is the duration of 9 billion periods of radiation corresponding to the hyperfine transitions between two hyperfine levels of ground state of cesium-133. This picture here is the NIST F3 cesium fountain clock. And the clock is so precise that it is expected to neither gain or lose a second in 300 million years. And that's a fractional uncertainty of the order of 10 to the power minus 16. Next steps are to develop these quantum technologies are to use, like, develop something which would have precision such that it won't lose or gain a second in the entire lifetime of the universe, which would be like a precision of 10 to the power minus 18 or 19. And once that is done, we would like to, the goal is to redefine the second definition of second. Now, one obvious way to increase the precision would be to use transitions at higher frequencies, because if you use higher frequencies, they allow us to divide the time into smaller intervals, which leads to better precision. Now, in addition to this precision, there's something also called the stability of the clock. And this is the instability, which is shown here. Now, stability, it represents how well the repeated measurements would produce the same interval, and it's directly related to the line width of the transition and inversely proportional to the transition frequency. So again, we get a hint that in the quest to define precise and stable frequency standards, what we should look for further, we should look for an atomic system that oscillates faster than the microwave transition between cesium atoms. And a number of different schemes are being proposed, which could be used for better clocks. One obvious choice is the optical clocks, because optical clocks are more accurate and stable. They are based on the forbidden optical transitions, and the oscillation in optical regime is 5 to 6 times order of magnitude higher than the microwave transitions, which leads to better stability and precision in the clock. Similarly, scientific community is also looking for clocks based on nuclear transitions, highly charged ions. Each of them offer an advantage or other as compared to the traditional microwave clock. So last year, we proposed a terahertz fountain clock based on the M1 transition between the hyperfine levels of the 4D 5-half and 4D 3-half state of niobium 4+, occurring at 56 terahertz. The clock scheme works as follows. I won't go into the details, but just give you a brief that after the cooling process of the clock transition, we use pulsed laser for the pulsed laser at 5.355 micrometers to achieve a population inversion, which is required for the clock transition working. Now, once this population inversion is achieved, and how do we know that this efficient population inversion has been achieved? We use another pulse laser, which is a very weak pulse laser between 4D 3-half and 5s half state, to check if the sufficient population inversion has been achieved. Once that has been achieved, all the lasers are switched off, and we kind of measure the clock transition. The proposal is very similar to the operation of rubidium atomic fountain clocks, and this probably is most likely the first fountain clock proposals in terahertz regime. And clocks in terahertz regime has various applications, which I'll be happy to discuss if somebody is interested. So in addition to proposing these atomic clocks with high stability and high precision, it's also required to assess that to what extent the clock can realize the definition of second. And the ideal definition of clock transition is based on ideal experiment conditions. However, in real experiments, there's always perturbation available around. And these perturbations, they cause shifts in the clock transition levels. So it's important that the transition frequency, it is corrected to account for the effect of these external perturbations. Now, various electric fields present in and around the experimental apparatus, like magnetic, electric, thermal, collisional, field gradient, gravitational fields, they all lead to various systematic shifts in the clock transitions, like the Zeeman shift or the quadratic Stark shift, and so on. So in our group, we also, as atomic physicists calculate these systematic shifts in the system. For example, this is the uncertainty budget for the niobium clock proposal we gave. It shows the different shifts and the choice of transitions between the hyperfine levels of the niobium clock, which I discussed. It allows us to remove the electric quadrupole transition, which is a very big advantage here. There is no shift due to the electric quadrupole. And also, since all the lasers were turned off during the clock transition, there are no shifts due to the AC stark induced by the lasers. The next in the uncertainty budget is the black body radiation shift in the levels. And these black body radiation shifts are the shifts due to the non-zero temperature of the apparatus. So the ideal definition of second is at 0 kelvins, but however, at room temperatures, the experimental apparatus, they kind of radiate some electromagnetic fields, which cause the shifts in the energy levels, which are termed as the black body radiation shifts. So next in the budget, uncertainty budget, are the Zeeman BBR and Stark BBR shifts due to the finite temperature of the temperature. So it turns out that these clocks can actually act as a very good temperature sensor. And they can measure even slight differences or variations in the environment temperatures and can be used in thermometry. So I would like to switch gears here. Professor Pathak, should I be taking questions now? Because this is the end of my first part of the talk and I'm going to start with the second talk, or I should take the questions in the end?
I think you
Question
can
would be
continue.
better to be taken at the end.
Okay, sure. So as I said, I would like to switch gears here and talk about a different, or maybe I would like to be vocal about this topic a lot because I'm very passionate and I was introduced with this topic at Perimeter and I found it very interesting. And we know that groups worldwide, including many in India, are working on building these quantum technologies, which I discussed very, very briefly, like what involvement my group had. The next question to ask is, where do we go from here? Like, the next challenge could be building a large-scale quantum computer or error-corrected system. Many are working on improving the precision of the existing technologies and accuracy of the existing technology and also proposing a better ones. But one very important aspect of building this technology is the ethical or the responsible aspect of it, which is not being talked about so much. Now, quantum technologies, we would all agree that they are super powerful and they can change a lot of things. So building and using them also brings up questions about what's wrong and what's right. So in the next part of my talk, I would discuss the risks and challenges that are involved in the not only the development, but also the deployment of quantum technologies, and also suggest a few recommendations, which I think, that's my thought, are important for responsible development of these technologies. So when I'm talking about a new topic like responsible quantum, we would, as a scientist, we would agree that we just don't want to jump into this field directionlessly. We want a strategic and a research-driven approach in this matter because it's very essential. So when we look around, can we see that there are some potential data or lessons which we could use from the existing technologies which are in place. And it turns out that AI is another rapidly growing and transformative technology with a lot of applications across various fields. While growth of this AI is exciting, it has raised, you'll all agree that it has raised very important challenges. The development and adoption of AI have taught us very valuable lessons that can guide us in responsibly advancing quantum technology. For example, many AI systems were deployed considering biases. They were trained using biased data, which led to discrimination. For example, in 2015, Amazon realized that its AI system was not rating candidates for their software jobs and other technical job posts in a general neutral way. And the reason was that the resumes which were submitted to company over the last 10 years most of them came from men. So it was trained on a biased data, which led to scrapping of their model altogether. Similarly, AI has trust and accountability issues. We'll all agree in this era of AI. For example, these AI-aided deepfakes, they have accompanied elections as well. I remember last year, this time in January, Karunanidhi, he made a very surprising appearance ahead of Indian elections. Although he had died in 2018, there were viral videos of Bollywood stars supporting some political parties, which were deep fakes. And they were reported. The culprits, they were arrested. However, despite the arrest, there was no comprehensive regulation in place. That was the sad part. And as of late 2023, there's a data that around like 85 internet users, they have the ability to spot the fake online content, which is very worrisome. So AI is developing at a rate faster than we have developed our regulatory measures. Another key lesson to learn from AI is the hype it created. So I'll talk about this hype and how it can affect quantum technologies development in my coming few slides. And we all would agree that AI development has often excluded diverse perspective. Like it's has many blind spots. It has black box algorithm. For example, the facial technology, which was developed using, which was used, which were trained using biased data, it led to very harmful effects in society. So in summary, I would say that regulations are lagging behind the AI innovation. And it's only lately everyone has started talking about AI ethics. So I just want to bring the same message that before it's too late, we should start talking about quantum ethics as well, because quantum technologies are developing and they would develop at a rate that we won't be able to make any control or regulations in future if we are not thoughtful about these issues now. So quantum ethics, according to me, is an interdisciplinary field, more of a philosophical and ethics background, but it also branches into physics, technology, social sciences, environmental studies. And it involves two different kinds of people. One are the ethics activists who would advocate that innovation should only enter market when there are no potential harms known. And the other are the tech advocates who believe that innovation should not stop at any cost. And we could mitigate the risk as and when they appear, or maybe sometimes they also choose to close their eyes towards the risk involved in innovation. Now, responsible innovators strike a balance between these two ideologies and believe that innovation should be pursued, but the potential risks should be managed. So when I talk about quantum ethics, most of the people, they give an idea that ethical ideas aren't universal. Like many label it as subjective. What is ethical for me might not be ethical for others or in different cultures. Like, for example, two predominant AI nations, US and China, they interpret liberty and privacy differently. Free speech is very important in US, while in China, unmoderated speech is not so welcome at times. We all would agree. So, but one important thing, which I think most of us can agree, is that maximizing the well-being of conscious being for sure is ethical and moral. So one can build quantum ethics model on an axiom that we need to maximize the interest of maximum. That should be our motto when we are developing the technology. And this quantum technology, since it affects the society, economics, politics in a way, and it should be built in a way that it benefits maximum equally. In order to understand like how it can affect the technology, we first need to understand what are the realistic impact of the quantum technology. Like in order to understand like how it's affecting the society, we first need to understand how could actually it affect in a realistic way. So if you remember in first few slides, I talk about three categories of quantum technologies. Here, I would only mention the transformative impacts of one of those technologies, that's the quantum computers. That's the closest to my work. And we know that quantum computers have transformative impact in various fields, like in optimization, they promise to streamline logistics, enhance supply chains, and also refine financial models. In healthcare and material sciences, they have capability to make breakthroughs by making these drug discoveries and also propose new innovative materials. In cybersecurity, quantum computing holds the potential that's like a fear monger, I would say. It has a potential to break the traditional encryption systems. Also, at the same way, like at the same time, it also paves way for next generation cryptography. And quantum computers can solve very complex physical and chemical problems in scientific community, which are, I would say, take more and more time using classical computers. And also it has effect on the global challenges, like it works with the nitrogen fixing and then has proposals using climate modeling and sustainability efforts. So it has a lot of transformative impacts. But while we are talking about developing these technologies for their transformative impacts, the question to ask is, while we are doing all this, are we maximizing the interest of the maximum, which is the common people, or are we working only for betterment of few privileged ones? And I'll illustrate this by an example, by showing that the quantum computer has ability to transform healthcare system, as I said, and also the financial world. Okay, so there is a class of quantum algorithms called the variational quantum algorithms. They are, I would say, a hybrid of quantum and classical algorithms designed to solve optimization problem. They have applications in quantum chemistry, like where one can simulate a quantum system and find its ground state energy. These algorithms are called variational quantum eigensolver, VQE. On the other hand, there's another special class of quantum algorithm called the variational quantum algorithm, quantum approximation optimization algorithm, QAOA. So this algorithm is used for optimization problem, like finding the efficient route or in finances. So VQE has significant application in pharmaceutical industry, where it can simulate molecular structure, enabling pharma companies to design new drugs faster and more cost efficiently. And the key players are Zepta, Computing, QCware, and Qubit. So all these are like million-dollar startups. On the other hand, QAOA is in high demand in finance sector for optimization of the asset allocation and portfolio management. So this is an area which is dominated by giants like the trillion-dollar giants like BlackRock. So just imagine a scenario that tomorrow Google announces that they have built a quantum computer which is capable of running both VQE and QAOA. The question arises, which of these two industries, the pharma or the finance, would be able to utilize this quantum runtime more efficiently? And the obvious answer is the trillion-dollar giants. So our research actually, in the end, is going to serve a few privileged ones, which already have the power. And the technology is not being used, is not being built for maximizing the interest of maximum. So we need to be thoughtful about all these things when we are developing these technologies. I'll also give one example when I talked about the hype, because this directly relates to the scientists who are working in building these technologies. Like, there are endless examples, but one which I would like to highlight is the fact that quantum computer has been a topic of concern for cryptographers and also security professionals for a while. Like, there's a hype where we say that building a stable or large-scale quantum computer has capability of breaking the modern crypto system. But we all would agree that quantum states are very delicate. They are easily disturbed. They lead to collapse. So are we talking about, like, when we are worrying about all these security issues, at this point of time, are we being realistically correct, or are we just creating a hype? So I would give explain this. These are just my thoughts, and I would just explain it by giving us few data that in 2019, researchers in Google and one of the other research institutes in Sweden, they estimated that a quantum computer with 20 million qubits would be able to break the RSA encryption. And it would take like 8 hours to do that. And currently, we are years apart from creating such a system. The best one we have done so far is the 1000 qubit IBM quantum computer in 2023. And there's an recent announcement by IBM. But still, we are years apart from creating a system to 20 million qubit system, which would be able to break this RSA encryption. So creating all that hype about quantum computers, breaking our encryption today is creating an unnecessary hype and fear. And hype is not so good. I'll give an example of the AI. We have witnessed similar thing in AI, which led to AI winters. And we should be mindful that similar hype in quantum could lead to something called quantum winters as well. So in 1956, at the Dartmouth meeting, it was predicted that AI would soon match or surpass human intelligence. And at that time, the computer, they were working on vacuum tubes, and they were filling entire rooms. We didn't have internet. We didn't have large data sets like today. So we didn't have the technology, advanced hardware. And still, that hype during that time, it led to massive funding for the AI researchers. And obviously, since we didn't have the infrastructure, we couldn't stick to the promises which we had made, which led to a long AI winter. Now, is now in the last few years with our computational advancement that AI has become a reality. The AI development could have been done faster, or that revolution could have been brought earlier if that we didn't have that we didn't have seen that AI winters. And I think we are repeating the same mistake with quantum computation. So quantum computing hardware is still in its infancy, I would say. We should be mindful when we are promising all these breakthroughs. And my recommendation, proposed recommendation, would be to avoid overselling our current capabilities. And the best way would be to design a metric which would evaluate how far is the technology from the real world capability of fulfilling its promise. Now, there are a number of potential risks of not adopting responsible and timely actions, like job market imbalance, underrepresentation of marginalized group. But I wouldn't be talking about all these factors. I would more talk about what role as an individual we can play in promoting ethical practices in quantum ecosystems. And when we talk about the role of individuals, there are two main individuals. One are the policymakers and the experts, like these quantum experts. And it's the responsibility of the government or policymakers to set regulations and policies to guide the development of quantum technologies in a more responsible way. But this should be done in collaboration with experts and public. That's really important. The government in this aspect should not build any regulations without consulting the scientific community. The role of experts, like quantum scientists and educators, should be to prioritize ethical designs. They should promote transparency. Most importantly, what I'm going to talk in the last 10 minutes would be the responsible quantum education or communication. So this aspect focuses on educating all interested parties which are involved in quantum innovation. The various interested parties which are involved in development of these quantum innovations are students, which would comprise our workforce, researchers and scientists, which are the developers of the technologies, and the technologies are being developed in their labs, public, who would be the users, and also the taxpayers who are actually funding these technologies, government and policymakers, who should collaborate with these experts to make regulations, and the tech or the industry, which act as a facilitator between the between the research which is conducted in quantum labs into the practical applications for end users. So as quantum experts, is our responsibility to involve all these interested parties and contributors and responsibly educate them for the development of these technologies. So there are several key components of this responsible quantum education, like ethical, societal, inclusivity, equity, environmental consideration. So I will not highlight all of these components here. I will focus on two of these since I'm a science, like promoter, science communicator. So I feel more close to responsibility of building a quantum force to support the industry trends and interdisciplinary education, and also responsibility of public engagement in the growth of these quantum technologies. So I'll just focus on these two aspects of responsible quantum education. So first and foremost, predicting the workforce needs for different domains like software, hardware, theory, experiment in quantum industry is very crucial. Like we should be able to predict the potential future trends in quantum industry so that we can educate our youth, we can educate our students about these trends, and they can make informed career choices, like which domain would have more workforce demand in future. That's really important. We should be training our youth not in just one domain of the quantum technology, like the experiment or the software, but we should predict the job market is like the trend of the job market. And one example is security, cyber security. Like 15 years ago, I remember institutes, they just used a word cyber in their program. It's people enrolled like mad, and cybersecurity really grew a lot. But once the critical and missing roles were filled in the area, the hiring slowed, but still we are producing so many cybersecurity professionals. So the potential risk in quantum technology is similar. If we train without consulting the industry and studying the job market, there could be skill gaps, and it would not lead, like it would lead to job market imbalance and slowed innovation and waste of resources. So one is really important, that we should train our workforces by keeping in mind the future trends in the job market. The second important aspect is that we should be creating an all-rounded force at this time. We should ditch the one-trick pony or like one-size-fits-all approach kind of thing. We should be training our workforce which is comfortable in all different pillars of quantum technology. By that, I don't mean that they should be mastering all the domains, but a foundational understanding of different areas across the field is really important for sustained innovation. This includes like basic knowledge in physics, computer science, mathematics, exposure to different areas within quantum technologies. Now, this approach would help students to make informed decisions. If they understand the whole ecosystem, they would be able to choose careers that fit their interest. And also interdisciplinary training helps scientists and engineers to communicate in a better way and develop technology efficiently. And usually I give an example when I talk to my colleagues here. I'd say that think of it like building a spaceship. You need engineers for engines, you need astronauts who understand navigation, you need botanists to grow food for your journey, but it's not that everyone is specialized in their area. Everybody knows a bit about the other areas as well when they are building a spaceship. And the most important thing, which I'm not going to talk about because this is something which mostly people talk about when they talk about responsible education, responsible quantum, it's that we should have a future, like we should think of a future workforce as a gender biased community. It's important that the current training should consider that aspect into account. So the other key component, one was the development of like training these workforces. The other key component, I really very close to my area or my, I would say, past experiences, is the responsible quantum education for public engagement. Now, the reason being that without basic understanding of quantum technology, public may struggle to actually know its potential benefits. Like lack of basic know-how of quantum technology could lead to skepticism and fear. And obviously, if the public, which is the end user, it is fearing the technology, it would hinder government funding and public support for research and development. And if public doesn't understand the potential of quantum technology, they may not use it as a user, and it could slow down the overall progress of the industry. So for sure, it could lead to reduced demands, like hesitation to adopt the technology. For instance, let's say we develop a fertilizer using some quantum simulations. Now, without understanding the potential for increased crop yields or reduce environmental impact using those fertilizers, farmers may be hesitant to adopt it. So we need to educate them. And also, if people fear or misunderstand the technology, then regulations could be stricter, which could lead to less innovation in the technology, I would say. So these are my few recommendations. One is outreach for public engagement. And in this case, I am a I'm a supporter that instead of inviting public to lectures, the outreach should be done by going to public. That's really more impactful and efficient. In order to train our students and youth, it's very important that we have a curricular which integrates quantum science and into the educational framework in early stages. It's like we don't have to explain them how internet works, but still every kid knows the bads and goods about internet. So similarly, we should be also educating our students early about these quantum technologies. It should be included in curriculum. And scientists are already engaging in these scientific talks. But what's missing is that during these conferences, at least we should have one session based on responsible quantum technologies. There are a number of global initiatives, like Europe is, I would say, the one which is leading in this area with its initiatives like these quantum flagships and the research institutes. Like US is also working on these. It has allocated a lot of funds for ethical research and development. Canadian initiatives have recently started. Like I'm part of the Center for Responsible Quantum Innovation and Technology called Circuit at Quantum Algorithm Institute, who are dedicated to creating these ethical frameworks and promoting responsible innovations. And there are many other institutes. The one which is mostly in highlight is the Open Quantum Institute at CERN. So in the last 3 slides, I would like to take this opportunity for a call of action working together towards building responsible quantum ecosystem in India. And with India's National Quantum Mission, I think it's a unique opportunity that we could actually lead the global effort in responsible development and deployment of quantum technologies. And we must establish centers like Indian Quantum Responsibility Centers which are dedicated to responsible quantum innovation. And these should be the key participants, not only just the quantum experts, but we should have social scientists, policymakers, representatives from environmental science, science communicators, EDI experts. Everyone should be part of that community or that center. And I think these are the key objectives. These are my thoughts. But if such a center takes into place in India, there should be more inputs coming from various people who are part of the committee or center. But we need to establish guidelines for best practices, and we should promote interdisciplinary research and also develop educational programs to raise awareness among our general public and even small, like high school students. So I would like to thank everyone for being so patient for past 1 hour and listening to this. And I'm open for more questions and discussions.
Thank you, Dr. Arora. And we're now, of course, this was actually multiple talks means it went from one area to another area, and I'm sure that students will have many questions. So anyone who has a question, please raise your hand or just unmute yourself and speak one by one.
So Professor Pathak, are my slides still visible? I want to stop. I think
Yes,
I
yes,
see.
it's visible.
I'll stop sharing now. Yeah, okay.
Now it's gone. So Ajay Kumar has a question. In atomic clock, which principles of quantum mechanics involve and how it works?
Okay. So so atomic clocks actually are clocks where I would say a tick in the clock is defined using atomic transitions. So atomic systems, they have these atomic levels, and the transition between these levels, they occur at very precise frequencies, which we kind of know to a very high precision. And when these atomic transitions, they happen at a particular frequency. We have the ability to find that frequency and then check how many oscillations of that frequency would correspond to a second. So once that number of oscillation happen, we count 1 second, second number of oscillations in the clock like atomic clock transitions, second, and so on. That's how the basic atomic clock works. Like basically, you're just counting how many number of oscillations in an atomic system correspond to 1 second, and you're just counting them.
So I hope this addresses Ajay's questions. Who else has questions? Please unmute yourself and ask. Dr. Singh, please continue.
Yes, first of all, thank you very much for the wonderful talk. Especially the last part I enjoyed because the earlier it is not my field. So, very simple question is you studied in India, you are working in India, and you are also in Canada. You have seen many countries. My question is, how big is the gap when we talk about quantum computer technology between India and Canada and China?
Very less to say about China. I have been there. They have built
Okay.
a lot of quantum technologies. What I saw there was lack of innovation, I would say. I don't know if that's, again, my personal opinion.
Yeah.
What they in China are doing, they're kind of replicating the technologies which are already in existence. So they are not, according to me, not building something new. That's past like 3 years, 4 years back. That's what I'm talking about. But they're really good in replicating those technologies and with a better improvement, I would say. In Canada, think IQC here at Waterloo is working with, which have a very dedicated institute just for building these quantum computers. In India, I think we started, but we started a little late. That's again my opinion, and people may differ. We have the potential for sure. That's really true. Especially the theoretical potential is immensely strong in India. We have started, but I think we still have gaps to fill in. And since we started a little late, so it might take some time. That's my honest opinion. Yeah. And
I can see
I
that.
believe here is that I feel people are communicating more with people, interdisciplinary fields. And that's how they are bringing up more ideas in developing these technologies. So it's not like quantum, the IQC is working as a separate identity. They are working with theoreticians at Perimeter Institute and other institutes. So they are collaborating with other fields as well, which is a very nice way of building any technology in a sustainable manner.
So I can see Shatish has raised hand. You can unmute yourself and ask your question.
Hello, ma'am. Hello, am I audible?
Yes, please continue.
Okay, so my question is from first part of your talk. So my question is how this atomic clock can be used as a sensor. Like if I want to sense the temperature, how this clock can be used.
So if you remember in one of the slides where I showed the black body radiation shifts, due to the clock proposal we made. Now, these black body radiation shifts, they are shifts in the energy level of the atoms which are being used as atomic clock, which are used in atomic clocks. So when we have a finite temperature of the experimental apparatus or the surroundings, according to Planck's law, there are electromagnetic fields produced, which we commonly known as the black body radiations, right? Anything at a non-zero temperature is going to emit electromagnetic fields. Now, atomic properties, they have a property that when they are exposed to electromagnetic fields, there are shifts in these energy levels. Atomic clocks, using these atomic clocks, we can actually measure these shifts in the energy levels, which are direct signature of the temperature of the environment. And that's how they can be used as thermometers or sensors. Like they have ability to sense the temperatures. Is that, I don't know if that is if that was a clear enough answer.
No, ma'am. It's clear.
Okay.
Yeah.
Any
I
other
have a
question?
query.
Please continue.
Can I ask a question?
Yes, yes, please
What
go ahead.
type of atoms are suitable to make it as an atomic clock?
So there are a number of considerations to be made. And there are different categories of clocks. For example, the present popular clocks, which are the passive atomic clocks, one very important condition for choosing the system is that it should have a forbidden transition, which should act as a clock transition. They are called passive atomic clocks. And for that forbidden transition, the state, so there are two states involved in the clock transition. The excited state should be a metastable state. There should be a population inversion possible. That's one condition. And obviously, that's like one important condition. And obviously, the lasers which are being used to cool and also study these clock transitions, they should be available for experimental ease. That's another one. And I think the most important one is that the line width of the excited should be small so that population inversion is possible. But there are other classes of atomic clocks which are called active clocks, where such condition is not like required, and all you need is that you have I'd say you have the technology to manipulate the atom. For example, for these active clocks, alkali atoms are a very favorite atomic system because we have available lasers to manipulate the atomic systems in that system.
And my second query is, you have discussed about that with the molecular level, some calculations in the molecular level, which can act, we can take an active role for, you can say that for the drug designing and all these things. So what type of simulation you want to mention there? Is it a DFT-like calculation?
So the algorithms are called variational quantum eigensolvers. I don't know if, I think they're not DFT based. They are based on solving the eigen. So I'm not an expert or I don't work in that area, but as far as I know,
That means ultimately,
again,
you are in that case, they are solving Schrodinger equation or not? That is my point.
yes, they are ultimately solving Schrodinger equation and finding the eigenvalues. Yes.
Okay.
Hello. Can I ask a question?
Yes, please.
Hello. Okay. First of all, I want to convey thanks to Dr. Arora for the nice talk. And my question is, I think you have talked about NB+4 ion for doing the atomic clock. And also you have mentioned that in the recent past or the recent days, nuclear transition is also utilized for design atomic clock. But my question is that what is the motivation to go for nuclear transmission? And what is the specialty of the ion N+4 to make this atomic clock or atomic to fulfill the criteria to making the atomic clock?
So for NB4 plus, I can definitely answer it because that's my field. And so these proposals different proposals other than the microwave clock, which is the cesium clock, which currently defines second. Giving these different proposals, there are different advantages. For example, switching to an optical clock, the obvious advantage is, since the optical transitions are happening at higher frequencies, you have better stability and better precision. For the terahertz clock, the niobium proposal, which I discussed, terahertz is a regime between the microwave and the optical. So it obviously has the precision better than the microwave, but less precision than the optical clocks. But these fountain clocks, the technology for these fountain clocks, which I said is the niobium clock, which we propose, they're already in existence. We know that very well. The cesium clock is an optical clock, is a fountain clock. So the advantage is, one advantage is that it's better than the microwave clock. We know the existing technology to make it, which is not very convincing, I would agree, but terahertz regime in itself is very important. For example, one application which we saw for terahertz clock was that they were really sensitive. They were not sensitive to the other shifts, but they were sensitive to the black body radiation shift. So they could act as thermal thermometer. And the other advantage is that most of the radiations, like the I would say interstellar radiation and terahertz regime, they need these clocks, especially in deep space probes where GPS won't work. So yeah, there are advantages of using different techniques. And if there's not advantage, I would say there is always a quest for scientists to work with different technologies. I don't know if that answer. For nuclear clock, I remember reading about it long time back, and it had the nuclear transition, which is based on I'm sorry, I really can't remember it. It was long time back. I did read it. That's not the area where I work, so I can't remember it exactly right now.
Okay, it's fine. It's fine.
Okay.
Thank you.
So there are a number of questions in the chat box. Shall I go ahead and answer them one by
Yes,
one?
there are two questions in the chat room, Vince.
Okay. So
And
there is a
one from
question.
Mudita, the other.
I
Please.
want to ask how to gain knowledge of different quantum technologies deeply, because I'm aware only a little bit about atomic clock and not about other technologies. So Mudita, probably I would first like to know what's your current status? Like, are you undergrad or a grad? And maybe
This is a MSc first year student who has just finished the first semester.
okay. So at your institute, I mean, your institute is amazing,
Yes, Vince.
building
She's our
amazing
student.
quantum technology.
That's why I know that she's in first year, Vince. So
Like on a personal level, if you're interested in the field, you should be reading more about these technologies, and there's so much available on internet. But always connecting to different people who are working in these technologies on personal level, if you could do that, always helps. So I really don't know how. What else? Like reading and talking to specialists is the two ways I can think of learning about that topic. Okay. How quantum superposition and entanglement enhances the stability of atomic clocks. I think atomic clocks in itself, they don't work on the principle of entanglement. What we require for atomic clock, but yeah, quantum superposition and entanglement, they are helpful for building quantum computers. And entanglement itself doesn't have any role to play in building of atomic clocks. And quantum superposition is a principle which is like unavoidable in any system. Any atomic system would be in quantum superposition. And the superposition, it kind of doesn't enhance the stability of atomic clock. So stability of atomic clock is dependent on, let me look at the slide. It depends on factors like the line width of the clock transition. So as I said, there are two levels involved in atomic clock. The excited level, it should have a small line width, and which leads to smaller instability, which means higher stability. And transition frequency should be higher. And experimentally, in order to increase the stability of the clock, you should be using more and more number of atoms in your experiment. And there's another factor called the observation time, which should be very high, like which should preferably should be as long as possible.
Is there any other question? I wrote in the chat room requesting others to switch on their camera so that we can take a group photo. So if some people have switched on, if others can also do that, it will be good for record. So, okay. So is there any other question? If not, okay. Dr. Singh, please continue. Unmute yourself.
Yes. So, Dr. Arora, you talked about the policies, how to promote everything, and most importantly, the gender balance. So when we talk about the gender balance in India, recently I wrote one book, or we wrote one book on the biography of Chandrama Shah. She is the first woman who became the president of the Indian National Science Academy. It took almost more than 50 years. In the case of theoretical, I think you are from theoretical physics. How is the position, especially in your university or Guru Nanak Dev University, the number of women compared to men, let us say only in the field of physics where you?
So GNDU, interestingly, has a very dynamic, I would say, the transition from undergrad, grad to faculty and PhD to faculty. It's like we have more representation of females in undergrad, grad.
Wow.
Even for PhD, I think it's almost 50-50. But when it comes to higher positions,
Yeah,
like faculty positions or higher positions, the female representation is really small. And that's very interesting thing which you brought, Dr. Singh, because we occasionally think about these gaps. What we usually miss is we miss to note the point where actually those gaps they start.
yeah.
What happens after PhD that women they leave science is something which we should be thinking about, and maybe supporting women at that point of their career would help them to pursue sciences and not leave it.
So just one more comment, because in the Western people, at least in our University of Oldenburg, they are talking too much about the gender balance. They have even special rules that the women, they should be promoted. Until the last year, out of 15 professors, there was only one woman professor. And this year, she left and they have found new persons. There are only men now. What I want to say is in Western culture, we talk sometimes too much about promotion of women, but the reality is different. As
I
you
agree.
were saying, when we go to a very high level, when the question of professors or managers, then the number of women is really very less. That is all.
That's right. And Perimeter recently had their director change, and it's a female director. What's really impressive about her is that she is a woman scientist, very accomplished one, who has a family, which is really unusual.
Yeah.
She has kids which are doing well in their fields, and her partner is also a very famous experimental physicist, which is really should have these role models. I agree. But I agree that Western culture, maybe this won't be liked by many, but what's my opinion, personal opinion, is that in Western culture, they have already taken care of the food shortage, poverty, and so on. Now, just to keep their minds busy, they talk about all these things. But at ground level, nothing important is happening. In India, we are still struggling with basic facilities. We have more things to worry about than talking about it. So here it's mostly talks. I'm apologizing if somebody gets offended by it, but that's my personal opinion, I would say. right? They have to keep their mind occupied. So they
Yeah.
talk about gender biases, and I have been in club meetings where they talk about uh, having I mean, like there are different issues which are they mention, and it's like surprisingly like what are they talking about? For example, one of the journal clubs, they were talking about how to make conferences more inclusive for fat people, which was like we would never think of issues like that because we have other things to worry about.
Yeah.
So, but it's mostly talk, and I still don't see a lot of women representation in Western universities as well.
Yeah, if I may, Japan, in India, we have many problems
Yes.
which we're trying to solve. So this also is included in those problems. So that is why everything is happening together. And
Yes.
so the women issue is also an issue which is being tackled at the same level as many other problems are being done. So that is why, for example, I am from IIT, and IITs, there have been special ways to include more women in the undergraduate, which is the engineering, where less women were there, but now the number has gone up. And so, and even in faculty, we have quite a good number. In physics, for example, in IIT Delhi, we have about 5 or 6 faculty members, females, out of 40 or something. So it's much better than what you have in Germany, for example. Dr. Singh, hi, this is Anurag Sharma, you remember? Yeah.
No, it's definitely improving over time.
Yeah. Yeah,
And
definitely.
as a student, what we have
But
seen
what
and
what
see now as
Dr.
a
Arora
teacher
is saying that the dropout after the PhD to the faculty is significant.
Yes.
It's significant. That has to be seen. Yeah.
That's true.
Yeah.
So we are almost at the end, and every good thing, good discussion concluded. This was very thought-provoking discussion, and I'm discussing quantum technologies for such a long, but we have never discussed ethical quantum technology or ethical developments and ethical issues in any meeting. And so that's something new for me also. And
it's a new dimension.
Of course, the talk has a technical
Actually,
part, and then we have
Pathak, I'm
yes, ma'am,
planning of building this I would say not community or center, something like a virtual center, and I have also talked to Professor Arvind about it. And maybe I have a proposal how to build this center in India, and I'll forward it to you if you're interested.
Sure.
Okay.
So that's nice, and this is the way it works. The entire talk is something which we expected, and when the way we plan that it will have some social aspects, some encouragement, some demonstration of good science, and at the end we discuss social issues also. So altogether, the idea of the talk, the way it is prepared, is quite fitting with the idea of organizing these lectures. And thank you for making it such a nice coincidence. And I would like to thank
you so much
everyone for
thank you very
joining
much
in this talk. And this is a series, so next talks will follow, and we'll expect you to join in the next talks also. So thank you everyone, and good night.
Thank you so much.
Good night.